This is problem A in chapter 7, and this is what it says. A golf ball strikes a hard smooth floor at an angle of 30 degrees and, as the drawing shows, rebounds at the same angle. The mass of the ball is 0.047 kilograms and its speed is 45 meters per second just before and after striking the floor. What is the magnitude of the impulse applied to the golf ball by the floor? And then in parentheses there's a hint. Note that only the vertical component of the ball's momentum changes during impact with the floor and ignore the weight of the ball. The hints here mean that the momentum in the horizontal direction is the same, and that's due to this kind of angle of reflection here, and it travels with its inertia to the right as it goes down and up, and there is no friction, and it's totally elastic, and there's no English on the ball, and so on. And then the other one, I believe, means that ignore the weight of the ball. It's kind of interesting. That as it falls down here, actually it should accelerate due to its weight and then decelerate on its way up. But they say, the outcome is the same either way, so let's just ignore it and assume that it's just before impact it's 45 meters per second, and after impact totally elastic, it's 45 meters per second. So anyway, because we're supposed to ignore the horizontal, that's why I'm just gonna look at the vertical. So as it vertically impacts, this here would be the vector down, and then here the vector up. And when you look at the geometry here, so we have an angle here and an angle here, and that's actually the same as that 30 degrees. And so for the vertical component, we would have to figure out that the initial velocity is in the vertical direction is the cosine of that 30-degree angle in here times the hypotenuse, because the cosine goes with the adjacent of the angle. So when I do that on the calculator, I come up with 45 times cosine of 30 degrees, and that comes out to 39.0 meters per second. So that's actually the number we need, and I guess we just go with two significant figures, 39 here, and actually that's a minus, and then here it's a positive 39 meters per second. Positive up. Again, that's due to we have to look for the adjacent, which is the vertical component, and the angle here, 30 degrees, and of course that's with the cosine of the angle times the 45 meters per second. Okay, let's see what else is given and what we're supposed to figure out. It says we're supposed to figure out what is the impulse, so I'm going to make a question mark here. What's the impulse? And then what else is given is the mass of the ball is given as 0.047 kilograms, and then the speed of the ball is given as the initial speed is given as negative 39 meters per second, as you see already that part of the calculation, and then the final speed is given as positive 39 meters per second. Neither the force nor the time are given, so it must be something else that we need. And in fact, the impulse can be written as force times delta t, or it can be written as the change of momentum, and apparently that's what we need here. So the impulse is going to be mass times Vf minus mass times initial. Whoops. Hold on. Mass times the initial velocity. And then the mass, as I said, is 0.047 kilograms, and then this velocity here is positive, and this velocity is negative, so we actually add this one to it, so we come up with a larger positive number, which makes sense because the momentum originally is down, and then momentum is up, so it has to get a positive impulse. Positive first to make up for this one here, the negative here to get it down to 0 as it stops here momentarily, and then again the same amount to get it up to this speed, respectively, momentum. Again, positive. So yeah, the overall number is going to be positive, and the units are going to be kilograms meters per second. So far so good as far as this problem is concerned, but I wanted to use this for something else. The ball is going down and therefore has a momentum pointing down, and then it rebounds and has a momentum up. However, we find, of course, in the chapter that it says conservation of momentum. Well, if the momentum is negative to begin with and positive after the impact, then where's the conserved momentum? There has to be some negative component somewhere else, and that's actually the floor. That means that the floor absorbed the double momentum in the negative of the ball, and I'm gonna show you this here in an animation. So here I have a ball that is being thrown at a wall. The ball has a mass of 2 kilograms and a velocity of -4 meters per second, and you can see that the momentum here is written as -8 kilograms meters per second. And then here the wall, I believe I gave it a mass of 400,000 kilograms, so it's huge compared to the ball. What we expect now from the ball is that it's being reflected with the same speed to the right and with the opposite momentum, so this one should come out to +8. But notice what will happen to the momentum of the wall. So I'm going to let this run, and here we go. And as we can see, the momentum has changed for the ball to a +8, but as I said, because of the conservation momentum, the original -8 has to be there, so as the ball acquires +8 for momentum, the wall had to absorb -16, and when you combine the two numbers, -16 plus 8 is indeed the original -8. So the momentum actually has the wall actually has a momentum to the left, and of course it's a heavy wall that's not very apparent here, and for all practical purposes it's actually not moving. But if I change the mass of it, so instead of having 400,000 kilograms, I'm just going to use 40 kilograms for the wall. So this is kind of like a paper thin wall almost. Okay, and here we go, and there you can see the wall itself is moving. And again, if you use these two numbers here, -15.236 and +7.236, it comes out to the original -8 kilogram meters per second. Notice that the momentum of the ball now is, as it returns here, is not the same in the opposite direction. It actually not only has given some momentum to the wall, but an appreciable amount of energy, and that's what, of course, what it lost here in velocity. On the first one, maybe I can, yeah, there we go. On the first one, what actually happens is that the amount of energy in the transfer is negligible, and that's why we didn't see that. Why is that important? Well, let me show you another example. First I have to reset this here, and I've got this out of the way. In any kind of collision between cars, in this case a car and a bus, notice that the bus, even though it's a whole lot heavier, more massive than the car, absorbs momentum as well, and we know that from any kind of collision. And maybe the car doesn't rebound, it's actually probably inelastic collision, but it kind of shows my point. So back to the original problem, the floor does absorb momentum, but and we have to, that's actually where it goes, so that momentum is being conserved. But of course the floor has such a large mass that it doesn't matter to the floor.